Hello and welcome back to the Steam Cycle lecture series for the SPG course. In this third section, we will quickly review some very important improvements for the Steam Cycle, their thermodynamic background and the merits that they add towards higher efficiencies. How do we run steam cycles in power plants today? First of all, they are all superheated. So we certainly want to have at least a bit of superheating, and indeed as much as possible of superheating into the steam cycle. There are two merits related to it. First of all, this raises the average temperature of heat addition. Looking back at basic thermodynamics, and remember we're only dealing with classical thermodynamics now applied to actual cycles for energy conversion, adding heat to the cycle, in this case, boiling steam, heating up the water to boiling point, evaporating the water into steam, and then superheating the steam as much as possible, as much as the materials and the temperatures involved allow us, would help work with higher temperatures. And in the cardinal sense, this means that we're raising the potential of the cycle to actually convert heat into power with higher efficiency. The second advantage is that in practice, we do not want to end up the expansion, that would be point S2, deep into the double phase zone. We do not want to deal with wet steam. This is a problem mostly because in mechanical terms, our machines today are not able to handle wet steam, or they degrade too quickly when wet steam, that would be droplets of water condensing into the steam flow, actually is involved in the flow inside the machine. The best example are rotodynamic machines, steam turbines that are used today in large power plants. We are not using piston machines anymore. And the blades in the turbines are eroded severely by those water droplets in the steam flow. So the target is to end the expansion, that would be point S2, somewhat close to the double phase line. That would be the saturated steam line. Not too far away from it, because then we don't use the entire potential for expansion, but maybe slightly inside the double phase zone, or at least on the double phase line. The rest of the cycle is pretty much the same, and you can find other diagrams out there on the internet or in books. This is just an example of how we represent the cycle in a real TS diagram. The actual cycles with superheat involved that we use today for power production are usually called Rankine cycles. And the Rankine name comes from a person. There was a Scottish engineer called Rankine. Actually, it had a bit of a complicated name. You see it here, and you can read about him in books, who actually, for the first time, theoretically proved that superheat is good for the steam cycle. In thermodynamic terms, again, because we increase the average temperature of heat addition. And if we try to represent it mathematically, the average temperature of heat addition would be some kind of a integral along the line where water is being accepting heat, or water being heated up to evaporation point, then all of it evaporated, and then the steam being superheated. The more we superheat, the higher the average temperature would be. But not only, the higher the pressures that we work with here, the more we would push the evaporation line mostly up towards the edge of the double phase dome, towards the critical point. So higher pressures, better efficiencies. We take it as granted today, but it can be represented easily in thermodynamic terms, and that's what Rankine did. Well, Rankine also is remembered as being associated to William Thomson and Joule and other guys in England in the old days, towards the middle of the 19th century. And actually, he gave his name also to the absolute temperature scale in imperial units, which is referred to as degrees Rankine, while degrees Kelvin, as you know, we use for the metric system. where exactly the average temperature of heat addition lies is not so important. Well, thinking about the fact that actually heating up the liquid water involves quite a bit of more heat than heating up the dry steam. While the biggest amount of energy involved into producing the working fluid or evaporating the water is exactly the evaporation process. So the average temperature of heat addition, whatever we do with the cycle, is somewhat close, but a bit below the evaporation temperature. Again, the more we superheat and the higher pressures we choose to work with, the average temperature of heat addition would grow or would increase. And the more we increase that, the higher potential we will have for converting the heat into power. At the same time, what we do in the condenser is also important. We have to now remember the second law of thermodynamics. We have to perform the condensation process at as low as possible temperature. In reality, the availability of cooling or heat sink that we have, that would be related somewhat to the environment around us, whether it's cooling air that we're using or cooling water. We will be limited by the environmental or the ambient temperature. And we have to stick to those temperature levels as close as possible in the condensation process. Working with high difference or a large difference between temperature of condensation, if possible far below 100 degrees, and the temperature of heat addition, the average one. Hopefully as high as possible. And you see, water is not allowing us to raise that temperature too much because raising it involves enormously high pressures. This is the main problem for the continued improvement of steam cycles today. If we want to push the average temperature towards the critical point as close as possible, or even to go supercritical, completely outside the double-phase dome, we have to deal with enormously high pressures, for which we don't have the materials. Reheat is one further step that we can add to the common steam cycle, converting it into something that has a higher potential, again, for conversion of heat into power. It is the same Rankine cycle, and today we usually refer to a Rankine cycle as any generic vapor cycle for power generation. If we add reheat to it, that would be simply a second superheating step. Steam expands partially in one section of the turbine, then is sent back to the boiler or in some other way is being heated up again to the same or to a similar, somewhat similar temperature as the main superheating step, and then expanded further to the lowest possible pressure. What we gain from this, again, is, first of all, a further increase of the average temperature of heat addition. We add more heat to the cycle, we force the steam to produce more work. And ending up the expansion somewhat, in the best case, outside or close to the saturated line, avoiding handling wet steam. Thinking theoretically about this case, if we have multiple superheating steps, just imagine, that would be a kind of approaching the Carnot cycle, or let's call it a quasi-Carnot. We can continue, or rather cut the whole superheating process into a large number, theoretically large number, of reheating steps. That would be an almost constant line of heat addition, constant temperature line, allowing us to perform, in theoretical terms, a best case Carnot-like cycle, meaning that we can achieve, hopefully, at least theoretically, higher efficiencies. Practically, this is not possible. Of course, it is possible, but it would not be economically justified, both in terms of having many different small steps of reheat, and that is small steps of expansion, would not allow us to use one big and efficient steam turbine as a mechanical device. And also in the boiler, sending back steam, which involves pressure losses that are not really represented in this idealized diagram, would actually incur losses that are much more than what we gain from the multiple reheats. So real power plants usually have one reheat. The best ones today have 2 reheating steps, not more than that. Feedwater preheating is another way to improve the efficiency in the cycle without at all changing anything in the steam parameters. The same boiler, the same condenser, more or less the same steam turbine. All the major parameters are the same, but still we can do something inside the cycle to improve the efficiency even further. And this something is usually called feedwater preheating. It involves extracting steam from the steam turbine, usually also called as bleeding points, and sending that steam into heat exchangers. The steam condenses, giving the large latent heat involved into the condensation process back to the liquid water. The main feedwater line in terms of liquid water is being heated up a bit before it reaches the boiler. It is difficult to imagine or to comprehend actually the merits of feedwater preheating. It is a type of internal regeneration of heat inside the cycle. Why we do that is not so obvious in terms of winning efficiency. But if we carefully consider the entire cycle, not only the steam section and not only the expansion line, but the boiler, whether or not it is a black box as here, we don't care how the boiler looks like and we don't care what the fuel is. It is completely irrelevant. But the point is that the boiler is in the picture here. And we consider the temperature of feed water that's being sent to the boiler. And also, of course, the main steam parameters coming out of the boiler. We can easily guess what the boiling temperature is when we know the pressure and the temperature of the outgoing steam. The boiling temperature would define the major amount of heat or energy that the water needs to get in the boiler in order to be converted into vapor. Going back to this type of diagram, actually we can see that, well, boiling water at higher pressures actually takes less heat than if we boil it at lower pressures. Here at lower pressures, we perform the condensation process. But again, it actually can give us, if we condense some of the steam at lower pressure than if we boil the same mass flow of steam at higher pressure, we can get more energy in the first law terms from that steam. Imagine the same mass flow at lower pressure than at higher pressure. So let's boil everything now at the highest possible pressure. Let it expand to a certain middle section. And using this reheat diagram, actually we can imagine that after the reheat, we extract a certain amount of the steam and condense it to take its heat and use it for feedwater preheating internally inside the cycle, integrated heat regeneration. Here we have 4 steps of those internal regeneration of heat. Steam being extracted, condensing, and after that it has somewhat in some way to be recycled back, whether cascading down to the condenser or pumped immediately back into the main feedwater line, it doesn't matter. We will try not to lose that mass flow, which is much smaller for each of those extractions. It is a much smaller mass flow compared to the large main mass flow of feedwater flowing in liquid form through those preheaters and being heated up. Each preheater is adding some temperature. Usually, well, it's a bit exaggerated in this picture here, but in reality it's from 20 to 40 degrees Celsius in each step, and we usually have several of those steps. In the end, we are sending much warmer water towards the boiler compared to what we get out of the condenser, the coldest point in the cycle. So we can think of it as if the energy we lost or the mechanical power we didn't produce by sacrificing a certain steam flow is gained in return back if we save fuel in the boiler by sending there preheated water rather than cold water. And the fuel we save in the boiler is actually much more in terms of energy compared to the power we lost when we sacrificed some steam. Instead of expanding to the end, it was extracted and its latent heat used for preheating the feed water. The more preheating steps we have, again, theoretically, the more efficient the cycle would be. In practice, usually there are up to 10 preheaters in big, large-scale power plants. The target always is to preheat the feed water as close as possible to its boiling point. And again, how many preheating steps there will be depends on what are the purposes of the power plant. If it's a warm condenser, maybe also supplying district heating, we wouldn't have such low temperatures here, but maybe around 100 degrees. So the room remaining for preheating is not that big. Or if we have supercritical parameters in the boiler, where the boiling point is even beyond 300 degrees, we would have room and definitely necessity to perform several stages of preheating and send to the boiler water with temperature as close to the evaporation temperature as possible, saving the boiler from involving energy into heating up the liquid water, but then using the fuel only for evaporation and superheat, while the preheating is taken care of the latent heat inside of through internal regeneration. The modern steam cycles actually can be quite complicated. They are nothing more than what we talked about already. Simply the components, the number of components can be much higher. The turbine can be cut in several sections. The boiler may involve superheat and reheat. The steam turbine may be situated in different shafts. The condenser will need cooling water, of course. The number of preheaters and the number of feed water pumps may be different. There might be different arrangements for internal heat regeneration in the cycle, again, to decrease losses and to decrease as much as possible the leakage of heat. And we will also need a deaerator. Now, the overall efficiency, and we're talking about the electrical efficiency here, or say the mechanical efficiency, it doesn't matter if you produce electricity or we drive a machine with the power we produce, is definitely dependent, the overall efficiency, on the, again, average temperature of heat addition, the temperature of condensation, which should be as low as possible, the internal losses or the internal efficiencies, or rather said, inefficiencies involved in each of the components, possible leaks, losses of mass flow, losses of pressure, thermal losses from components, and so on and so on. All of these aspects can be improved and are being continuously improved. Even today, when we think that everything has reached the end of its development, actually not. It is still possible to improve the efficiency of existing steam cycles and to build new steam cycles several percentage points better than the ones or than the power plants existing today. One very important component, which is very often actually neglected or simply forgotten when we do the calculations of steam cycles, but which is very important and completely inevitable in the real practical power plant, would be the so-called feedwater tank. There are three main purposes with the feedwater tank. First of all, this is where the working fluid is sitting when the cycle is not operating. It's a big tank of water. As simple as that. When the cycle is operating, again, most of the liquid water is staying in the feedwater tank. It is lying there. The tank acts as a buffer in the system, accepts any kind of makeup water that you need to inject in the cycle if you're losing mass flow, and also acts as a preheater. So if we look at the complex modern steam cycles which our power plants are using today, they would involve everything that we talked about. The boiler itself, now we can disregard how exactly it looks like, but definitely there would be some fuel involved or other kind of heat energy transfer from something to the working fluid. Superheat, reheat in one or two steps most often. Then the steam turbine ending up in several sections, producing or not electricity or driving some other machinery. Condenser, preheaters, one or many of those, or none in some cases. A feedwater tank, any other kind of heat exchange in order to integrate a bit more of internal regeneration or to take care of certain other thermal leaks and bringing them back into the cycle, and many other auxiliary components that we very often do not show in the simplified drawings and diagrams that we work with. For example, the pumps, usually called here this one a condensate pump lying just under the condenser. The main feedwater pump, physically always to be found under the feedwater tank. Maybe other pumps returning the condensate lines back to the main feedwater line. Valves, pipes serving the turbine, the boiler, or the cold end of the cycle, and many, many other small components. The overall efficiency of the entire steam cycle or the entire steam plant would be a function of, again, the average temperature of heat addition, which should be as high as possible, the condensation temperature, that would be the temperature of heat rejection or the heat sink of the cycle, which should be as low as possible, the internal losses, or rather say the internal inefficiencies of all separate components, the complexity of the circuit, the number of feedwater preheaters, and the more they are, at certain point they would lose their merit. Of course, they would also involve certain losses. Any other losses related to heat leaking to the environment, mass flows being lost, pressure being lost along pipes, and so on. All of these aspects can be improved enormously. Even if today we do run very, very, very efficient steam cycles, still there is room for improvement in terms of several percentage points. The electrical efficiency of modern steam plants can be improved further. One very important component, sometimes disregarded and sometimes neglected, but definitely very important and present in all kinds of steam cycles, would be the feedwater tank. It has several names, but most often referred to as feedwater tank or FWT in diagrams. Its main purpose, of course, is, just imagine it, when the cycle is not operating, this tank is simply storing the working fluid. All the working fluid would be water in liquid phase, and it would be sitting in the feedwater tank. In practice, this is demineralized, actually treated water. We don't want to lose it. We have invested some energy indeed to provide demineralized water. So it is stored in the feedwater tank. When the cycle is operating, the feedwater tank has two major purposes. First of all, it actually works as a feedwater preheater. It keeps the water in it, and again, when the cycle is operating, most of the working fluid is still in liquid form and it's still available here in the feedwater tank. We keep it hot, and this is done by again, the feedwater tank operating as a preheater, taking in hot steam from an extraction or sometimes directly throttled from the boiler and using it to saturate the water inside. And on the main diagram, you see that the feedwater tank lies somewhere in between in the cold end of the cycle, cutting the feedwater preheaters, better say, into a low pressure side and a high pressure side. The main feedwater pump situated right under the feedwater tank, and it operating at certain or somewhat higher than atmospheric pressure, clearly defining the low pressure and the high pressure side of the cold end. The third purpose of the feedwater tank is to act as a deaerator. Deaerating means that we are trying to kick out all kinds of dissolved gases from the water. And this process needs to be run continuously, because imagine that a condenser is working in a vacuum pressure. So we go below atmospheric thanks to the availability of cooling water. The condensation process is performed far below atmospheric pressure, deep vacuum. Air inevitably leaks into the condenser. Whatever we do, there will be some gases leaking into the cold end of the cycle and then easily dissolved in water. Oxygen actually is dissolved in water comparatively easily, being a gas. That's how fish is breathing. And running a hot cycle with or having oxygen molecules in the water would end up into corrosion. So continuously, the working fluid in the steam cycle will need to be treated or post-treated by kicking out the dissolved oxygen. This is easily done, again, by simply heating up the water. So keeping it in saturated condition in the feedwater tank, and then venting out certain amounts of steam, well, sacrificing some mass flow of steam, which hopefully entrains also the dissolved gases driven out from the liquid water simply by being heated with direct contact with hot steam, would actually help keeping the oxygen levels or the gas dissolved levels in the water at sufficiently low levels. So because of that, the feedwater tank is often called also as an open preheater. It is a direct contact preheater, and then it's also an open preheater, venting out the dissolved gases, which are driven out from the liquid water. Again, the feedwater tank is inevitable in every steam cycle and will be lying somewhere here, in between preheaters, if we have any, or in between the condenser and the boiler on the liquid side of the cycle. Some practical points when it comes to really running steam power plants, and for which we don't have time in this lecture, but we will consider in different lectures. Each of those points here actually deserves a lecture of its own. First of all, the large number of actual components involved in the steam cycle make it very, very complex. And in many cases, it is undesired, really, as a way to convert heat into mechanical power, because simply it's always complex. This is one of the reasons for avoiding running steam cycles in very small scales. Even if your plant is very small, you would again need all those auxiliary components. And even if you get rid of efficiency improvements like reheat or feedwater preheating, you would still need all the major components, all the other hardware. The whole plant would still be big in terms of size compared to power output. You'd still need lots of pipes, also redundant pipes, and hundreds, even thousands of valves in a large power plant. Plus the fact that you're working with high pressures, which involves some kind of regulatory measures and maybe permissions and so on. Then the working fluid is a big question. Why we are using water usually? Well, it's the cheapest and the most common material. It actually is one of the best working fluids existing. But in certain conditions, water may not be the best one. And we're going to talk about low temperature cycles, very often called as organic Rankine cycles, where other fluids other than water are better suited. Anyway, for large scales and for cycles involving high temperatures and higher mass flows, it is always water that is the best choice. Cold start is very tricky for steam cycles. Imagine you have a large plant, everything is cold, big boiler, big steam turbine, big feedwater tank. You have to heat all this thing. And we're talking about enormous components. So the thermal stresses involved need to be avoided, plus that heating up this enormous mass of hardware will take usually hours and in most cases days. Starting a cold steam cycle and ramping it up to full power very often takes a few days. If not, even if you start from a hot condition, it might take a few hours really to run everything into full power. Very different from gas turbines or piston engines or any other devices that we might replace the steam cycle with. But again, in very large scales, the steam cycle is the best choice. Cooling water is another important issue. We take it for granted, but very often it's simply not available. If you're building a steam cycle out in the desert, you may not even have the cooling water to provide for the heat sink. You may choose to run an air-cooled condenser, which will be an enormous construction. And again, you will not be able actually to run into deep vacuum the condenser. You would like to work with water. Now, decreasing the size of that heat exchanger, which is one of the biggest hardware devices, and trying to, if you are in an environment which is already prone to arid cycles, you would like to avoid using cooling water as much as possible, or save it as much as possible. Providing the cooling, whether it would be a cooling tower, or a lake, or a river, or a sea, well, it's a lecture of its own, but again, you must think about it before you start composing the entire cycle. The partial load, when it comes to steam cycles, is another very important aspect to be discussed. Usually steam cycles are not very good in part load. If they have to run often at variable loads, they will need to be designed for that. And in most cases, typical steam cycles are not designed. They are not expected to run in part load, and they are not designed for that. Practical going into part load conditions would involve steam throttling before the steam turbine, just destroying the enthalpy of steam by decreasing the pressure without production of work, or running the boiler at a sliding pressure. Decreasing the pressure in the boiler together with the mass flow decrease, actually providing less mass flow to the turbine and lower enthalpy at the start of the expansion, hopefully keeping the end of expansion at the same conditions. Usually a blend of the two, like a mixture between steam throttling and sliding pressure, is being used, together with decreasing mass flow. Efficiency very often drops quickly if we go to deep part loads. Say that a steam cycle is made to operate at 100% loading, doesn't matter how big exactly that is. Usually the efficiency down to 80% load is fine, or it's more or less same as the main output or as the nominal conditions. But below that, or if we go, for example, to 50% load, which is very often the case, if the cycle is being run in variable conditions, would actually involve more or less half the efficiency. Other off-design conditions can also be tricky. For example, the conditions on the cold end. you suddenly don't have the cooling water available, or something goes wrong. If you cannot provide the cooling or the heat sink in the condenser, the cycle stops. Or if you're not able to cool at the same rate the condenser as the boiler operates, well, the power output will decrease immediately. Other change of conditions may happen in the boiler itself. The boiler conditions may be affected by other than operator-defined load change, fuel imperfections, pressure losses, and so on. To summarize, it suffices to say that partial loading is a difficult point for steam cycles, and if they are supposed to work at variable conditions, they will need to be specifically designed for that. This is the end of the steam cycle lecture. Thank you for your attention, and we can talk about many other details in the following lectures.